So let's start section 10.3, regression analysis. And forecasting. Okay, so the regression equation regression line is a line of the following form. Well, it's y equals mx plus b, and this is for a sample. And y equals mx plus b for population. Okay. And so this is the line that best fits the data. It minimizes the squares of the error. It is the least square regression line. So we'll make some assumptions. That these pairs of data are from a random sample, this bivariate data, and this will be quantitative data. That the scatter plot of this data looks like a line, looks like it could be approximated like and outliers suspected, outliers that are suspect are discarded. Any outlier will greatly affect the regression line. So if any of them are suspected to be errors or anything, then you would certainly throw them out. Next, I have to assume that the random variables x and y and that these come from normal, I'll say our normal random variables. And they have the same variance and the mean and their mean. lies on the regression line. So these are the assumptions that I make. Okay, so I have here that the slope, B1, is just equal to n. I'm going to do this obviously just for a sample. N sum xy minus sum x sum y. So we've already seen this sort of calculation when we're looking at the linear correlation coefficient. That's the same numerator. And the denominator, well, we've seen this too when we looked at the variance. That was actually the numerator for the variance. We could also say that, well, so this is the formula I'm going to use, but it's also a ratio of these covariances. And if you want to put it in terms of the correlation coefficient and some covariances, I can write it in the following fashion. Or I could write it as, again, in terms of the correlation coefficient and some covariances. Okay, the y-intercept can be written in the following formula. Sum y sum x squared minus sum x sum xy divided by n sum x squared minus sum x squared. But usually we use the fact that, well, y equals mx plus b. And so the fact that the mean lies along the regression line. And so that will simplify. Once you've calculated B1, then B0 can be calculated. Just using this, so that's obviously a much easier calculation. So I usually just use that calculation. So I can probably write it. Let's see. I can also write it, well, so let me just say that I call this simple regression. Where you have b0 plus b1x. So there's only one variable x. Multiple regression, if there's more than one variable. Say b0 plus b1, maybe I'll call it x1, plus b2, x2 plus however many you want. Let's say bk, xk. So that would be multiple regression. Now, maybe I'll write the equation. So rather than have solved it, let me write the equation. For simple regression. So it's actually sometimes easier to solve. Well, usually it's easier to solve than the actual formula I just gave you. So b1 sum x squared plus b0 sum x equals sum xy. And then the second is b1 sum x plus b0n is equal to the sum y. Okay, so that's the equation, the system of equations that you would solve for simple regression. Let me do an example. Determine the regression line for the following set of data. And maybe I'll write it this way. $34, $35, $4, $37, $5, $36, $32, $6, $34, $5, $30, $10, $38, $3, $42. Okay. Okay, so basically we're going to want to solve the following system. Of linear equations. Okay, so it's going to be b1 sum x squared plus b0 sum x equals sum xy. So I'm going to have to figure out the sum of x squared, the sum of x, the sum of xy. B0 sum of x plus B0n is equal to the sum of y. So I also have to figure out the sum of y. Okay, so let's do this. So x, I'm going to list it this way. Okay, so 35. $34, $30, $38.40. Okay, so let's do this. Okay, now let's just multiply first and second columns, square the first column, and then that's really it. Is that 9 for y? That's a 4. There. Sorry, sort of got in the way. Okay. So let's multiply these together. So 140, 185, 192, 170, 300, 114, 80. I'm going to have to add these up. Square that. 12, 25, 1369, 1024, 1156. Oh, actually, I should do this. 900, 1444, 1600. Let me actually. Isn't there a 36? No. There's no 36. Oh, there's a 30. There's a 30 here, but no 36. Actually, what I should do is let me do this on my, let me do this on my TI 83. Okay, so actually let's do this where hopefully, I can do this easily. Okay, it's acting pretty good. 35. Input the data. Into L1. Input the data. Okay. Into L2. Okay. And so then you do L1, L2. Actually, let's do it in L3. Good. And then L1 squared. Store that into L4. Okay. And then you view your data and you go, voila, here it is. 140, 185, 192, 170, 300, 114.80, 1225, 1369, 1024, 1156, 900, 1444, and 1600. So good. That's all of your data. How's you get the X-score column? Sure. So let's quit that. If you look, I just did L1 squared, stored it in L4. Okay? So I just squared the first column and put it in L4. And then if you multiply the first, the X and Y, L1 times L2, that gives you L3. Okay. Good. Now, oops, hit the wrong thing. Now, let's find the sum of all these. So, go to list, math, sum of L1, 246. Sum of L2, oh, that was obviously a typo on my part. Okay, there. Did it actually go 1? Okay. Sum of L2, good. 35. Sum of L3. Oops. There it is. Sum of L3 is 1181. 1181. And the sum of L4 is 8718. And so, just plugging these numbers up here, I want to solve the equation, the system of equations, 87. Wait, what do you keep doing? Okay. Let me just check. Is everyone still able to see me? It didn't blank out on your end, did it? So 80. So no. So that means you. Let me re-ask the phrase. Can everyone still see me? Yes. Okay. Good. Okay. So let's go back. So it's 87, 18, B1 plus 246 B0 is equal to 1181, along with equation 246 B1 plus, there are 1, 2, 3, 4, 5, 6, 7 numbers. 7B0 is equal to 35. Okay, good. And so let me solve the system. So I can just multiply the first equation by 7, the second equation by negative 246 to get rid of the B0, and I'll solve for B1. And so I get 510B1 is equal to negative 343. Divide both sides of my equation by 510. And so I get B1 is negative 343 over 510. Next, let's figure out B0. Well, that's just equal to the mean of y minus B1, the mean of x. And so I get the mean of y. Well, that's just sum of y over n minus B1. The mean of x is sum of x over n. And so I get 35 over 7 minus negative 343 over 510 times sum of x. 246. 246 over 7. And so B0 is just going to equal, plug that into your calculator, 51,114 over 1785, reducing it. And so I get the following regression equation. Y equals 51,114 over 1785 minus 343 over 510 x. Just call it x. And that is your regression line. Okay. It's the count of how many bivariate data there are. So the number of rows, or, well, columns in this case, I guess, because there's 1, 2, 3, 4, 5, 6, 7 pieces of data. So it's how much bivariate data there is. Okay. Okay, let me do the following. Okay, so following example. So I guess determine a whole bunch of little things. The mean of x, the mean of y, the variance of x, the variance of y, the correlation coefficient, and the regression line for each of the following. So I'll give you some different sets of data. So this is okay. Let me go back up. There. Okay. A little down now. There you go. Okay. So let me look at the following. So let's call, so this will be 10, 8, 13, 9, 11, 14, 6, 4, 12, 7, 5. Okay. Okay. There it is. Okay. And for y, 8.04, 6.95. Got it. Okay. 7.58, 81, 33, 96, 24, 26, 84, 82, 68. Let's do the next one. I think it's the same. 10, 8, 13, 9, 11, 14, 6, 4, 12, 7, 5. Nine point 14, 8, 4, 7, 4, 7, 7, 2, 6, 1, 0, 1, 3, 1, 0, 1, 3, 2, 6, and 7, 4. Okay, and then the next column of data. Okay. Oh, 2, 2, 3, 3. So same. 10, 8, 13, 9, 11, 14, 6, 4, 12.75. Okay. 7.46. 7.7. 7.4. 1.1. 8.1. 8.4. 0.8. 3.9. 1.5. 4.2. 5.3. 7.3. And lastly, X4. And Y4. Okay. 8. 5.8. 7.6. 7.1. 8. 8.4. 8. 4.7. 0.4. 2.5. 5.0. 5.6. 9.1. And 8.9. Okay. Let me wait a second while you write all those numbers down. Then I'm going to unfortunately have to input them into my calculator. And I'll probably call this L1, L2, L3, L4, L5, L6. Okay, so I can plug them into those first 6 columns. Okay, so let me do that. Take me a second to do this. 10, 8, 13, and you should also do this yourselves. 2, 4, 6, 10, 11. Let me just check something. There are 11 numbers. Good. Okay. Just paranoid. And now let me put in everything into L2. So 8.04, 6.95, 7.58, 0.81, 8.33, 9.96, 7.24, 4.26, 10.84, 4.82, 5.68. Okay. Let me check if these are good. They're the same size. Okay. Let's see. Let me do L3. So 9.14, 8.14, 8.74, 8.77, 9.26, 8.10, 6.13, 3.10, 9.13, 7.26, 4.74. Put that into L3. Okay. See if they're the same size. Good. Let's do L4. Seven 7.46, 6.77, 12.74, 7.11, 7.81, 8.84, 6.08, 5.39, 8.15, 6.42, 5.78, 73, L4. Oops, let's see what I... 7 point, what the heck is that? 12.74, 7.11, okay, I moved it much too far, somehow. And I have to insert a comma. Okay, let's see if this works. Uh, 6.08, yet another comma. Okay, insert comma. See if this works. Aha, okay. Hopefully that was L4. Let's just check if that's L4. Yes, it is. Okay. And let's see if they're the correct sizes. They're of the same size. And lastly, L5. Okay. I think I blanked out for a second, so I'm going to do that. Okay. 8. Store that. And L5. Let's see what the dimension is of L5. See how close I am. I have 10 numbers. Oh, I need one more. Okay. Need one more number in L5. I accidentally hit the wrong button. That's got to be it now. Okay. L6. Ooh, I wonder. I think L6. Did I must have I must have put all the numbers into L6. Ooh, I don't have to do any more numbers in L6, do I? Okay, that's luck. So 1. Okay. So 6. They look all correct. I wish I would have known that I already had all these numbers in there. Okay, so let's quit. Okay, so all those numbers were in there. Okay, so um, now let me determine some differing values for these. Okay, so let's figure out the mean. Okay, so stat L1 var stats of L1. Okay, so if I look here, I have the mean is 9. The variance is, oh, let's call it x1. Okay. So to find the variance, I'll just go to vars, go to statistics, go to the standard deviation and square it. They'll give me my variance, which is 11. Okay. Good. Let's do that also for y. Okay, so let's do this for y. One of our stats for L2. What in the world? I have no idea how I got there. Okay, so one of our stats L2. Okay, so I get 7.09. Okay, 7.5. There. So y1 bar. The mean was 7.5. 0.9 with a whole bunch of 0.9s repeated. I'll just sort of make it shorter. And then the variance is 4.127. 29. 269. 269.091. Okay, good. Let's do this for, well, the second one. Well, obviously the x's are going to be the same, so I know that the mean is 9 and the variance is 11. Okay, so let's do the mean for that. And that was stored in L3. Sorry, I had to remember it's in L3. And so let's do this. And L3. 7.05, okay. 7.5. 0.9. And the variance is 4.127. 4.127. Six two nine 091. Oh, I wonder if those are probably reversed, because then it'll be the same. Okay. Now let's do it for, oh, okay. Now let's figure out the other mean. So third one, mean's going to be the same, and so will the variance. And let's do the mean and variance. And I stored this in L4. $7.5 and 4.12262. 2262. And lastly, maybe I should, those are the ones, those are the threes, now the fours. Okay, so the mean, well, I know what that is, that's 8. And there's a typo. It was a typo. The 1, 2, 3, 4, 5, 6, 7, 8th number down. 8th number. Typo. Let's look at the 8th number. eighth number is 19. Okay. Typo. So that eighth number there was a 19. Then it comes out nicer. Okay, so let's do one of our stats. In this case, that's got to be L5. So the mean is 9. And then the variance. We're going to have a hard time with that particular number, fitting it in, but, and so this is going to be 11. And then I guess on the next line, I'll put the y's. So the mean and the variance. So let's look at the mean. That'll be the sixth thing. That'll be this L6. Ah, 7.509. Oh, 009. They did it for all of them too. Okay, and let's look at the variance. Is 4.123. $249. 091. Okay, good. And then lastly, let's figure out the R's, the regression lines. So to figure out the regression line, let's do linear regression. And let's do the 1 and 2. So L1, L2, 5, 3 zeros. 1, 2, 3 zeros, and then a 9. Five. Okay. 3. And then 4 zeros. Before the 9. Okay. And then we want to figure out R, I believe. And so R, this is a 1. R is 0.665. 4245. 4245. 424595. Okay. Let's do the other one. And so 0.5. Three, and then 3 zeros. Three sixes, so 6 is 6, 24, 242. 0, 3, 3, 7. Do it for y3, x3, y3. Okay. That'll be L4. '99, then 72s. 99s, then 72s. Oh, 99. 7, 2. And lastly, 3 sixes and a 322. Sorry, 3.00 24 245. Okay. Then lastly, 816. Was I looking? I was always looking at r squared, wasn't I? Doesn't matter. I'll call these r squares. X3, Y3. I looked at r squared. 3 sixes, 32. 40. And lastly, the last of the bunch, that's 5 and 6. It was 5 and 6 I just did, right? 5 and 6, good. Okay, so 4, 3 nines. Okay. 3, 2 zeros. 17, 27. Okay, and then 3 sixes and a 7, 0. 7072. 569. Okay, so after all that, what we notice is that all the means are 9. all of the means for the y's are 7.5, approximately 7.5. All of the variances are 11 or 11. Yes, please allow some time to copy it. Okay, yes, I was just quickly summarizing. Okay, all the variances for the y's 4.127, 4.12. So you notice that these are all sort of all the same numbers here. And for each of these y's, so all, of course, 1, 2, and 3, I guess I should say, is 3 more or less to 2 decimal places plus 0.5 to 2 decimal places. So what you notice is that all the summary statistics, the mean, the variances, all the correlation, and the correlation coefficients, I didn't write those down, and R is equal to 0.666. So all the means, all the variances are all the same for x's and y's. All their regression lines are all the same. Again, to uh, like 2 decimal places, they're all the same. All the correlation coefficients are all the same. So, everything looks the same for them, except that they're actually suspect. So if you actually look at these, let me wait 1 second to be sure if everyone has all these down. Okay. So now if I look at, so let's go back up here. So here is this set of data here. So if I draw a nice little scatter plot, yeah, just do the first one. Let's do a nice little scatter plot. Let's do L1, L2. Okay, let's graph it. Nope. Let's clear that. Okay. Minimum, X minimum. Oh, let's say the minimum X goes 0 to 20, 4 to 13. That's all fine. Then it should be a nice plot. Let's see. Okay, good. So this is what the graph looks like. Good. Let's actually, and so if I look at that, that's a nice plot. And so if I drew a regression line, and let's draw my regression line, I'll see that it actually should be a nice, good fit. Oops. And so, my regression line is that L1, L2. Good. Let's go to here. And let's go to vars, statistics, go to the equation, and let's do my regression line. Okay, good. So let's graph this. So if I look at this, my regression line goes nicely through all those points. So that's nice and fine. So this is good. So for this first set of data, we've got a whole bunch of, it's good, and our regression line is correct. So this is a good fit. So this is x1, x2, x1, y1. So regression line is a good fit, and it's appropriate. Okay, good. Now let's look at the next one, which is let's look at 4. L1, L3. Three. Okay. And so let us plot this. Let's go to my equation. Let's plot that. Okay, good. Let's go to my stat plot. And put in L1 and L3. Good. Let's graph this. Oh, what did I mess up on? Oh, I didn't clear it before. Stupid. I had more than one equation at the same time. 5. Sorry, I was distracted for a second. 1. Okay, good. Let's graph that. Uh-oh. Uh-oh. If I look here, these points, it has the same regression line and all that, but these points don't lie along a nice linear curve. They're actually parabolic. So the regression line that I gave was completely wrong. I shouldn't have done that regression line. That was inappropriate. So you shouldn't have used linear regression. So if you would have looked at the plot, you've seen it looks something like this. And so do not use linear regression. That regression line is really quite inappropriate. What you probably should have done is quadratic regression. So if I would have done some sort of quadratic regression, should have gone along something that looked quadratic. Okay? And so, if I would have done that, clear it first, and then looked at my regression line, okay. Then, if I would have plotted it, it would have looked much nicer. Sorry about that. Here, wait 1 second. You still copy the first graph? Yeah, the first graph is nice, yes. So the very first graph is nice. And it really should be appropriately used. Oh, why didn't it say squared? It's a square. Okay. Okay. Next. Let's look at the next one. X3, Y3. Okay. And so if I look at that one, and so let's go to X3, Y3. So it's L1, L4. Okay. Let me just check for 1 second. X3, Y3 is L1, L4. Is L1, L4, yes. That's L1, L4. Let's go to the stat plot. And so I want L1, L4. L4. Okay. Oops, I forgot to input that. Okay. So let's do vars. Fifth equation. Regression equation. Good. And so you look at this, and unfortunately, this part is linear, but there's an outlier here, so the regression line is actually the wrong regression line. And so because of the fact that you have an outlier, all your points lie along a line with a different slope. And so you've gotten the wrong regression line. So it looks something like this. And you did this regression line, so it's the wrong regression line. Due to an outlier. So unfortunately, this outlier gave you a wrong regression line. And now let's look at x4, y4. Okay, so that's 5 and 6. So 5 and 6. Okay. Let's put in the regression line. And we want to plot 5 and 6. L5, L6. So L5, L6. So if we do that, unfortunately, again, this is wrong because it's a vertical line. Again, there's an outlier, and so again, this is wrong because of an outlier. So all the points look like this, and we have this sort of regression line. So again, it's a wrong regression line due to the inclusion of an outlier. Okay, so you should check that the data more or less lies along a line. Then, if there are outliers, you should take out your outliers. Otherwise, you're going to get a wrong line. And of course, if it's not linear, then you cannot use linear regression. Yes, this will be available later today. Okay, good. So that really finishes off section 10.3. Let me go on to section 10.4. Actually, let's wait 1 second to be sure everyone has this. Okay, so let me go on to section 10.4. Variation. and prediction interval. Okay, so confidence intervals of variables so if we do a confidence interval, it really is an estimate. So confidence, and so maybe I'll say it this way: confidence intervals are estimates, are interval estimates of parameters. Well, the same sort of thing, prediction intervals are again just the same interval estimates but rather being estimates of a parameter, they are estimates of a variable. Okay. So let me do the prediction interval for y. So the prediction interval for y is just the predicted value of y plus or minus some error, where the error is just the t-value, the t-critical value, times the standard error, 1 plus 1 over n plus n x0 minus the mean squared n sum x squared minus some x quantity squared, where the standard error is the square root of y minus the predicted value of y squared over n minus 2. Okay, so the explained and the unexplained variation. Okay, so maybe I'll do a little graph. There's fine. Okay. Okay, let's scroll down, I think. Okay, so say I'm looking at this point, and it has, say, this value. Okay, so this is the predicted y. Okay, so this distance here is the explained deviation. This here is the unexplained deviation. Y minus y. And then, this whole well, from here to here, that is the total deviation. Okay. Whereas this was the explained deviation, and that was the unexplained deviation. And the sum of those explained and unexplained was the total deviation. Okay. Okay, let me scroll. Oops, too far. So, the total deviation, well, let's write this. Y minus the mean is equal to, well, y minus the mean. And I'll write that as, let me add and subtract the estimate. Okay, so now I have that the total deviation this first quantity on the left is just equal to, well, this explained deviation here plus the unexplained deviation. Oh, of course, I wrote that wrong, didn't I? Because that is this amount. Because when you add them, you get that. Oops. plus, there was a typo there, plus the unexplained deviation. Uh-oh. I think I blanked out here for a second. Let me get back. Okay. Plus the unexplained. Deviation. Okay, so the total variation will just equal the explained variation plus the unexplained variation. And so the sum of y minus the mean squared, sum of y minus y bar squared plus sum y minus y hat squared. Okay, good. So I have here that the total variation is the explained variation plus the unexplained variation. Now, we make the following definition. Well, the coefficient of determination. Which turns out to be the square of the linear correlation coefficient, is just the sum of y with the sum y minus y bar squared. Okay, and so this is just the ratio of the explained variation to the total variation. So if we're going to be looking at the square of the correlation coefficient, that actually tells us, you know, how much of the variation we can explain. So let's do an example. Suppose x is the shoe length and y is the height. And the correlation coefficient is 0.813. Okay. then what can we conclude? Well, then we know that r squared is 0.661, more or less. And so that says that 66% of the total variation in height so if I look at your height, well, I can explain 66% of how people's heights vary by just looking at their shoe size. So just looking at the shoe size, so 66% of the total variation, in height can be explained by the shoe size, by your shoe size. Whereas the other 33% cannot be explained. By your shoe size, by your shoe size, by the length of your shoe. So if I look at just your shoe size, the length of your shoe, uh, I can explain. I can more or less figure out how tall you are. I can figure out the differing sort of, and I can be so confident, uh, you know, I can that I can explain like so 2/3 of of what makes your height just by looking at your shoe size. Okay. Um, so that's a coefficient of determination. And that, oh, okay, so we told you the prediction interval. Um, so that was the prediction interval for y, for which, I should say this, for which x equals x naught. Okay. Let me give you some confidence intervals. So the confidence interval for beta so beta is 0 is equal to b0 plus or minus an error, where the error is t times your standard error, which we gave you above, square root of 1 over n plus n, sample mean squared, n sum x squared minus sum x squared. Okay. and beta 1 b1 plus or minus e, where e is equal to t, standard error, over the square root of the sum of x squared minus the sum of x squared over n. And this is with degrees of freedom equaling n minus 2. Lastly, confidence interval for the mean of y for all values of y for which x equals x naught this is just going to equal take the value of y plus or minus an error, where the error is equal to t times your standard error, square root of 1 over n plus n x0 minus x mean squared over n sum x squared minus sum x squared, with the degrees of freedom equaling n minus 2. So that finishes off section 10.4. Okay, let me go on to section 10.5. Section, you probably didn't get to it yet then. Question? Or just actually, nope, just typed in something. Okay. Section 10.5. Oh, last part. Yeah, yes, I will. Sorry. Hopefully that's good. Okay. Thank you. Okay, good. Yes. Section 10.5, correlation and regression. Analysis at a glance. So in this section, we just sort of redo everything we've done. So I'm not going to write all that down. It's basically just a review of everything. But so recall we had multiple regression. And so this will be a linear relationship between one dependent variable and multiple independent variables. Let's say x1, x2, to xk. And so the general form would be y equals b0 b0 plus b1 x1 bk xk. So the adjusted coefficient of determination So in this, we adjust the coefficient of determination to account for the number of variables and for the sample size. So we'll adjust this so that it takes that into account. Okay, so I have that r squared is equal to 1 minus n minus 1 over n minus k plus 1 times 1 minus r squared. Okay, so again, there are k of these variables, and n is your sample size. So we have to readjust r when we have it. So this is just readjusting r to account for the fact that we have a lot of variables. So that really finishes off, yay, section 10.5. No. Let me go to section 10.6. Yes, it was. Lots of fast, easy points there. Okay, let's go on to section, and the next one too. So some of these are really fast, easy points. Let's go on to the next section. Oops. Section 10.6. Whatever. Okay. Sorry, I had to close some windows. They didn't like all my windows open. Okay. Oops. Section 10.6. Correlation. And regression. Analysis. With Microsoft Excel. So, if you want to find the correlation coefficient, you would just write correlation, correl, and then whatever columns or rows you put in your variables. To find B1, just B1. To find B0, you say intercept. And to find Y, you would say forecast. Okay. So let's say we're looking let's say, I don't know, let's pick some numbers. Would I have something 10.4? No, how about 10.2 or 10.3? Sorry, I'm looking back for some numbers to plug in. Let's look at this. Of course, that's is that a straight line? No, let's not pick it. Well, it was a straight line, but okay, so let's do this. Here it is. Let's put in some numbers here. Oh, I see. I've got to put in some numbers. Let's say 1, 3, 5, 2, 7, 12. Of course, this was, let's do 13. Okay, so let's do that. So it won't be exactly. So the ones I had from before was, it would have given you exactly a line. Okay, so let's try to find R. So R. So we just say correlation. And let me pick these. Yeah, I didn't do anything yet. Correlation of these and those. Okay, so that's, again, I made it almost exactly 100% align. And if you wanted to figure out the slope, so B1, the slope, you would just say slope of known y's. Oh, well, it goes in a different direction, doesn't it? That'll give you your slope, it's around almost 3, and then your intercept, you would just say intercept of each of these. And there's your intercept. Should be close to 0. Okay, and suppose I want to find y at, let's say 4, because I don't have 4. Okay, then I could do forecast spell it correctly. Okay, so let's say 4. And then you put in your data. And you should see, yes, somewhere about 10. Okay, good. So that's how you would input this data, input these into Excel to figure out all the different values. Okay. So that finishes off. Here are the commands. So that finishes off section 10.6. Let's, oops, sorry. Yeah, put those numbers in. Yeah, put those numbers in. Shouldn't take that long. There aren't that many numbers. And nicer. And nicer numbers. Okay. There you go. Yeah, I was like, 200 is a better. You can actually see things. Okay, you guys are probably done now. Got it. Okay. Good. So after this off, section 10.6. Oh, this is just too easy. Let me go on to section 10.7. extended topics and proofs for correlation and regression analysis. Um, they just basically talk about multiple regression, which we've already done. So that really finishes off section 10.7. There's really nothing in 10.7. So that was it. Just the name of the. So let's go on to. So that finishes off chapter 10. Let's go on to appendix. We did appendix 1. Appendix 2. So I'm not going to, I'll just continue with this. Appendix 2. So this is on analysis of variation. So analysis of variance. Section 2. I guess A21. Introduction. Okay, so analysis of variance is abbreviated by ANOVA. Okay. So analysis of variance. And if you ever see the word MANOVA, that's multiple analysis of variance. So ANOVA is well, the variance ascribable to one group Okay. ANOVA is based on the F-test. ANOVA was first described by Fisher at the beginning of the 1900s. Again, Fisher was not was a agrarian, so a lot of these terms come from plants. The studying of the how if you look at I don't know, say you're planting a field of corn or whatever. You go through the forest, you notice that there's a lot of variation, and every plant looks different than the other plant or whatever, and maybe you want to see if there's more sunlight here as compared to there, how does that affect, the way that these plants look, how tall they are, how this, how that. And so a lot of the terminology will be that of, uh, you know, looking at plants. And so other people further on started looking at it, but they were in other fields, so they gave other terms for the same sort of thing that we're looking at. So what you'll notice is sometimes there'll be multiple names for the same thing. If you're not, planting corn or whatever, then this is not really, you know, the term you would use for, a patient in a hospital or something. So they're slightly different terms, but they all mean the same thing. We just give them slightly different names, depending on, what field you're in. Okay, so the assumptions are, let me do this. That the observations are independent. So we assume independence, and we have to assume normality, their parent populations, from which the observations are taken, are normal, and that the variance, treatments, and environmental effects are additive in nature. Okay. So some of the basic questions that we're going to try to answer. And so in chapter 7, we looked at one mean and saw, is it equal to some value? In chapter 8, we looked at two means and saw, are these two means equal, or maybe equal to some, the difference is equal to some differing value. Here, one of the questions are all the means from several populations? Are they all the same? So maybe, is mean 1 the same as mean 2, the same as mean 3, you know, same as mean, up to maybe you have 12 populations. Are all their means the same? Or maybe are they not all the same? And so you look at that and see, and try to answer that. Next are all the means from several treatments on one population Are they all equal? So we try to answer that. And lastly, do several treatments. Have a common effect. Okay, so that really finishes off our quick little introduction. Let me go on to section 2. The meaning and importance of ANOVA. Okay. So just recall the F-test, well, the F distribution. So again, F for Fisher. And so the probability density function just looks like some constant. So it's just some constant here. Times, again, this constant is such that the area under the whole curve is 1. And so it is F to the power nu1 over 2 minus 1 divided by 1 plus the ratio nu1 over nu2 F to the power nu1 plus nu2 over 2. Okay. Okay. And we had that the F-test had a test statistic for testing the equality of two population variances. Well, the test statistic, if you recall, was F was equal to S1 squared over S2 squared. Okay. So that was the test statistic. Okay, good. That really finishes off section 2.2. Let me, yes. Yes. Okay. Hopefully you're done. Okay, so you're done, right? Yes. Okay, so let me go on to section uh, 3, one way, analysis of variance. Okay, so in one way, analysis of variance, um, we're going to be testing if several population means are equal. And I can split up the total variance into two pieces. So first, the variation between classes. Next. And so the variation between classes, this is due to assignable causes that can be detected and controlled. And this will involve finding variances of means. Next, the variances, the variation within the classes. This type of variation is really just due to statistical variation. It's just due to chance. Um, this is calculated using all the sample data and is really not affected by the different means. Okay, so the requirements, the assumptions. Populations have normal distributions, or at least approximately normal distributions. Next, populations have the same variance. Next, the data comes from simple random samples of quantitative data. Next, I assume independence. Next, the different samples that these different samples are from populations that are categorized in only one way. Okay, so let's recall a few things from chapter 8 and see that this is actually very similar to what we did. So let's recall. In chapter 8, we were looking at the difference. Well, actually, let's do it this way. If two means were equal, or if they were not equal. Okay, and of course we had some level of significance. Then we used an F test. Okay, so uh, the statistic, the test statistic, was this test statistic. So the test statistic well, for determining the pooled or unpooled case, so we had to check if these variances were equal. So to check that, we had to look at S1 squared over S2 squared. And for the pooled case, so suppose that they were equal. Then we had the pooled case saying that the pooled variance was just a weighted average of the variances over the degrees of freedom. So I can say that this was just the sum of the degrees of freedom. Well, let's say I. In this case, it was just two of them over the sum of these degrees of freedom. Okay? And actually, the degrees of freedom, I guess, was if you added up all of them, it was n minus 2. Okay. So this is sum. Okay, so that's what we had from before when we tested. And I had that, I guess my sum of my degrees of freedom was this. Okay, which is actually the number is n minus 2, and that's actually how many populations we had. Okay. Okay, so now ANOVA. Here, the null hypothesis is that the means are the same. Alternative hypothesis is that they're not all the same. And of course, you had some alpha. Now the test statistic is going to look like this. So the test statistic actually look almost identical. So my test statistic is going to be F is equal to S of T. Oops, did I go too fast? A little up. Yeah, sorry about that. Probably here. Sorry. Okay. Wrong way. Okay, so the sum of the squares for the treatment sum of the squares of the error. So the variance due to the error with degrees of freedom for the treatments for the factors is k minus 1. We have k factors, k treatments, and where the degree of freedom due to the error is n minus k. Notice above, when I was talking about two means, k was 2. So this looks very similar to what we've had before. And now, look at this. This will really look very similar. First, the variation between classes. Oops, 1 second. I'll be back in 1 second. Okay, now I should be back. The variation between, where am I? Variation between classes I want. Sometimes we use this notation is the sum of each of the sample sizes, the means for each of the samples, minus the mean for all of them, squared, all over your degrees of freedom. So that's your variance. The variation within classes, this is the formula that I gave you above when we did this in chapter 8. And so sometimes we say put a subscript of W because it's within. Above we had a subscript of B because it was between. Sometimes for the error or for the treatment, so we put E's and T's. But they all mean the same thing. This is the sum of the variance, degrees of freedom times the sample variance. All divided by the sum of the variances. And if we look at that, that is the exact same formula that we had right here. Exact same formula. So it's the same formula that we had back in chapter 8. And I actually first gave you this formula back in chapter 2. So we actually did this back in chapter 2. So, well, sometimes we'll just say this is equal to since the sum of these is n minus k, the sum of the degrees of freedom. Because there's k of them. Okay, actually maybe I'll show that here. Since your degree of freedom obviously for treatment that's obvious because there's k categories, so degree of freedom is k minus 1. Degree of freedom for the error is sum of each of the degrees of freedom for each of those k categories. And so that's just the sum I equal 1 to n of n sub I minus 1. So this is just the sum of n sub I equal 1 to k minus sum of 1 I equal 1 to k. But if you add up all of these sample sizes, well, it should be the total sample size. If you add up 1 n times, if you add up 1 k times, you get k. And so that's why. Okay. Same reason we always got n minus 2 for the case of when we're doing two samples. For looking at the difference of two sample means. Okay, so let me give you some notation. X of I. This is just the mean for the ith one. So it's the mean for each, for the ith category. Okay. This is the variance for the ith category. Okay. Oh, it's 2 o'clock. In about 10-15 minutes. Okay. The mean. Yes. The mean. When I don't have an I, it means the mean of all the means. This is the average of the averages. So it's the of all sample means. And so this is just equal to the sum, let's call it Ni. So it's just the average of the averages. K is the number of categories. K minus 1 is degrees of freedom. Among the classes. N is the sample size, total sample size. It's the sum of all of the sample sizes. N minus K is the sum probably have to scroll back up. Yep. There you go. Okay. N minus K. Okay, so sum of squares between groups. Sum of squares between groups is sum Ni x minus x squared. Oh, here, wait. I equal 1 to K. This is sum of squares between groups. Between the classes. Sum of squares within sum of squares is the sum degrees of freedom variance squared for all of the K categories. Sum of squares within the groups. The mean, sum of squares between the groups. the mean, sum of squares between the groups, is, well, over your degrees of freedom. So this is the sum, I equal 1 to k, n I, xi minus x squared, all over the sum of n, it's k minus 1. All over k minus 1. So this is the mean. Sum of squares. Between groups. Okay. One more. A mean, sum of squares within group. Yes, I'm going to do an example. That's what I'm doing. Okay, so this is over n minus k. So this is a sum to k over sum to k. So this is the mean. Sum of squares within the groups. Okay. So let's do an example. Wait a second to be sure you've written this down. So I can do an example. I put like 5 examples. I'm not going to do that. Probably just do one several ways. I think I'll do that. Okay, so let's do an example. The ages of top executives in 3 major corporations are listed below. Okay, so let's look at their ages. So this is Corporation 1, so 49, 58, 55, 60, 62, corporation 2 is 61, 59, 58, 54, corporation 3, 56, 63, 60, 48. Okay. So, use analysis of variation. So analysis of variance at the 1% level of significance and determine whether or not why is it okay whether or not the average age of top executives at these corporations differ significantly. Okay, so let's do this. The null hypothesis is that the average age of the first corporation, same as average age of the second corporation, same as the average age of the third corporation. Alternative hypothesis is that they're not all the same. Alpha is 0.01. This is going to be an F test. You'll always be right-tailed. Alpha is 0.01. The degrees of freedom of the numerator is, well, there are 3 categories. So degree of freedom for the numerator is 1. Degree of freedom of the denominator maybe I should do it. Which did I do it more? Treatment error? Well, or within, between. I'll do it as treatment error. Okay, so this is equal to n minus k. There are 2, 4, 6, 8, 10, 12, 13. So there are 13 ages there, And there are 3 categories. So it's 10. You can look in your table. I forgot to bring it up on this computer, but look it up, and you get 7.56. Okay, so let's complete this. And this is called an ANOVA table. Okay, so source, treatment error, some squares, degrees of freedom, mean, some squares, and finally F. So let me do that. That's pretty big for that one. Okay, so let's figure out each of these. Okay. So, well, let's do this 2 ways, I guess. Let's put all the data into this. Okay, so let's put all this data in here. And so let's clear that. Okay. So 49, 58, 55, 60, 62. Put that into L1. Oh, come on. $49, 58, 55, 60, 62. Put that into L1. 61, 59, 58, 54. Put that into L2. 56, 63, 60, 48. Put that into L3. Okay, good. Okay, so there it is. So I just put all that information in there. So now let me calculate each of these. Degree of freedom for treatment, or I've already done that. Degree of freedom for treatment is just k minus 1, which is 3 minus 1, which is 2. Let's put a 2 there. Now let's try to find the sum of the squares. So let's figure out the mean. So the sum of the squares for the treatment is going to be the sum of the individual sample sizes times the means. Okay. Okay, so this is just going to be, maybe I'll write it all out. This will just be N1 times x1 minus x squared N2 plus N3 3 minus x squared. Okay. Okay, so let's look at this. And I guess, well, this is just going to equal the sum the average of these. Okay, so this will be whatever this is. This is actually from chapter 2 we did this. N1, N2, N3. It'll be easy to calculate it this way. For N1, it's N2 plus N3. So let's get each of these. So sample sizes. So stat L1 var L1. What the? Why am I there? Clear. Of L1. Okay. And so that's 5 and 56.8. 5, 56.8 plus that's 5 of them. Hope I can fit all those numbers here. Let's do it for L2. So for L2, the mean is 58. And there's only 4 numbers there. So 4 and 58. And for the last one, it is 4 and there's 56.75. 4, 56.75. I can't fit that there. $56.75, yes. Okay. And so, let's plug this into our calculator. So I get, and why is this? Okay, that was all that time. So 743 divided by 13. Okay, good. Okay, so I can plug that into here. So it says that is equal to 5 times the mean was 56.8 minus this guy plus 4, 58 minus the mean plus 4, 56.75 minus the mean, and you should plug all that in there. And you get, let's see, so 5, 56.8 minus over 13. Plus 56.75 minus 743 over 13. Okay. So you should get 4.142307692, which you put in your table. 4.14213079692. And now you divide the first column by the second column, so I'll do that sort of out of step, but I have a nice thing to divide. Okay, good. So now let's do the error. Oh, and then just putting down what I had in the table. Okay. So now let's do it for the error. So the sum of squares for the error is just the sum degrees of freedom. Ooh, the variances. Oh, I didn't write down the variances. 1 to k. I forgot to write down my variances, but that's fine. And so that's could be first degree of freedom, first variance. Okay, so this is equal to degrees of freedom for the first guy is 4. Okay. Let's figure out what each of these are. Well, so I'm going to have to go back here to figure out what that was. So that was degree of, so I did for L1, I forgot. So L1, that's the standard deviation. So let's figure out what the variance is. 25.7. Next, it was degree of freedom would be 3, since there are four people there. Let's do it for L2. And the variance is 8.6. Okay. Degree of freedom again is going to be 3. And let's figure out what the variance is for the last one. So for L3, for L3, 6.5 squared, that would be nice. It will be 42.25. So let's plug that in. That's a nice number. 4 times 25.7 plus 3 times 8.6 with a whole bunch of 6's plus 3 times 42.25 gives me 255.55. Okay, good. And then my sum of my degrees of freedom notice it's 10, and I got this by a different calculation. It's the same thing as what I did when I did this so I did a different way, but gives the same answer. So notice the degree of freedom is 10 and 255.5, 5, so 25.555. Divide it, obviously. Okay. And so 1 second. I guess I blanked out for a second. Okay, now I'm back. Why are they so long? They're not long at all. 1 second. I'm done. And so, these aren't too bad. And so, I have that my error, that the mean sum of squares for my error is 255.55 over 10, 25.555, and then lastly, f. F is just the ratio. So you just take those two numbers and divide them. And so, you just take these two numbers here and divide them, and we get, so finally, I get my test statistic. And so, I get 0.081046 9124. Good. 0.08106 9124. And so that's my test statistic. And now you go, oh, okay. We're way out here. So we're at 0.08104699124. So we're definitely not in the rejection region. So I do not reject the null hypothesis. So do not reject null hypothesis. And so yes, yes. I'm not really sure what that was. Too much for spelling. Yes. Oh, okay, okay. Sorry. Um, okay, there. Yes, there is insufficient. Statistical evidence. And I'll scroll back up in a second to reject the claim that each of the means are the same. Okay. So that's probably good for a few seconds. And then I'll show you another way to do it. And you'll be amazed how fast it is. No, actually. Okay. So another way to do this is we actually put all, let me look back up here. Hopefully you can see this now. So you see all this stuff here. I could have done it a little faster had I done the following. Okay, good. all I had to do is go to Stat, Test. Oh, come on. Test, ANOVA, L1, comma, L2, comma, L3. Hit enter, and there it is. Ah, oh, look at all of this. Degrees of freedom. Here's for the factor, the treatment. They call it factor here. Sometimes they call it factor, sometimes treatment. And so for the factor here, it's 2. Degrees of freedom is 2. There it is right there. Degree of freedom is 2. Next, the sum of the squares is 4.1. There it is, 4.14230769. They don't give you the 2. The mean sum of squares, here it is, 2.0711. There it is right there. 38, well, 5 rather than 46. The F value, here it is, right on the very top, 0.8 10469,124, exactly the same. P-value, we didn't figure out the p-value, but we could. Now notice, look at the error. Here it is. Degrees of freedom is 10. There it is right there. The sum of squares, 255.55. There it is. Mean, there it is. So they filled out all the table for us. They actually gave us the pooled variance, but we didn't calculate the pooled variance. And there it is. Now, they give us the p-value. Since the p-value that's certainly greater than, what was it, 0.05, we certainly reject the, do not reject the null hypothesis. So, if you did it on your calculator, on the TI-83, obviously some of the calculations would have been faster. That finishes off section 2.3. Section 2.4, I'm going to skip because that's really long. It's much longer than you want. It's much longer with much more calculations. Let me just do one more because it'll take about 2 minutes. Copy what you wrote. Scroll way down. Like to here. Like to there. How's that? Let me just check. Yes. Okay. No free points for 2.4, but they'll be virtually free points for 2.5, just like it was free points for the other ones. So 2.5 will be really nice too, because 2.5 will be really short. Done? Finished. Okay, everyone's done? Okay, good. So now what I'll do is I'll go on to section 2.5. So section A 2.5. Which says analysis of variance with Microsoft Excel. Actually, section 4 is much longer and much more. The notation is much worse, so we won't go over that because it take much too long. Okay, so analysis of variance with Microsoft Excel. I'll do the same example. And I'll put in all the data into Excel instead. Let's put in the data into. So and I don't care. Maybe I can do it either way. So corporation. Sorry. I'm tangled up. Okay, so stop. I'll call this Corporation 1. 49, 58, 55, 60, 62. That'll be it for that one. Corporation 2. Actually, I should have called it Corporation Corp 1. Okay. Corporation 2, 61, 59, 58, 54. And let me make this a little bit bigger. Corporation 3. Corporation 3, 56, 63, 60, 48. Okay. And now I'll do this. I'll go up to Tools, go to Data Analysis, One Factor, ANOVA, Single Factor, Input Range. These are grouped by rows, and labels are in the first column. Yes. And what is alpha? 0.01. 0.01. Output range. To wherever. Okay. Yes. And you're done. So there it is. So notice how nice and fast it is. Okay, so all the stuff that we got from before, here they are. Here's the ANOVA table. Here are the numbers we calculated from before. Here are these numbers before, you remember. Here we divided. So we calculated these with a little bit of work. It wasn't bad. And then the degrees of freedom was easy. Then we just divided the 4 divided by 2 was 2. The 250 divided by 10 was 25. The 2 divided by 25 was 0.08. And then here was the critical value. And here was a p-value if you wanted to find it. So certainly 0.08 is certainly much less than 7.5. And so you do not reject the null hypothesis. And certainly, and so the p-value also was a small value. It was a very large value, much larger than 0.01. So certainly we did not. It was not in the rejection region. And that's it. So notice it actually gives us other things. All this stuff that we used in the calculator. If you remember, we had a whole bunch of little side calculations we had to do with the TI-83. Here are all these little side calculations, and so you can figure out all that other stuff that we did. And that's it. So that was section 5. And that's it for today, and that's it for the course. Give those to me. Give your lecture notes to me on Sunday to get your extra credit points. Any questions about anything? Anything else you want to show? You want me to show you so you can copy it? Everyone's good with copying? Scroll a little bit. For this guy, for the Excel spreadsheet, correct? Yes. Okay. So that's the Excel spreadsheet from the very top. Maybe if I made this 150, it'll be easier. It'll fit everything. So now you can see everything. So all you had to do is go up to Tools. Of course, I'm assuming that you loaded the analysis package. Okay. Okay, so I guess that's it for today. Let me stop, if I can stop this from taping. There it is.